Welcome to the introductory colloquium series on the ECT STAR scientific workshops program. The intention of these colloquia is to introduce the topics of the workshops and publicize them to a wider audience. Today's colloquium will be given by Enrico Scomparin and Ralf Rapp and is related to the workshop Exploring high-muB matter with rare probes. This meeting is scheduled to take place in October 2021. So let me start by introducing today's speakers. Enrico Scomparin is an experimental physicist and an INFN staff member in Torino. He's first worked on hadronic physics and intermediate energies at the Saturn accelerator, and subsequently in the field of ultrarelativistic heavy ion collisions at CERN, the NA50, NA60 and LS experiments. His domain of interest is hard probes of the quark-gluon plasma, and in particular heavy quarkonium production. Recently, he's been coordinating the preparation of the proposal of the NA60 plus experiment at the CERN SBS, and he's also associate editor for the European Journal of Particle Physics C. Ralf Rapp then received his PhD in 1996 from the University of Bonn in Germany, and after holding positions at Stony Brook and Nordita, he joined Texas A&M as assistant professor in 2003, and he's been full professor since 2010. Ralf and his group conduct theoretical studies of spectral and transport properties of hadrons in hadronic matter and quarks in the quark-gluon plasma, and their relation to the QCD phase diagram and signatures in heavy ion collisions. He's received several recognitions for his research, including the NSF Career Award, Best Award by the Humboldt Foundation, and the APS Fellowship. The topic of the colloquium is motivated by the heavy ion programs at RIC and LHC, which provide unprecedented insight into the properties of QCD matter at high temperature and small baryon chemical potential. The region from moderate to high muB is of crucial interest for the understanding of strongly interacting matter in the QCD phase diagram toward higher baryon densities. And this domain will be probed by several existing or planned facilities. Particular interest here are the studies of hard and electrokinetic probes, as they are sensitive to the whole evolution of the collision. In the colloquium, the basic aspects of studies in the high muB region will be reviewed, followed by an assessment of the present theory situation for the study of dilaptons, heavy quarks, and quarkonium. And finally, the status of projects aiming at such measurements will be discussed, with an emphasis on the NA60 plus proposal at the CERN SBS, the forthcoming CBM experiment at FAIR, and the future running of the HADES experiment at GSI CIS.
Good morning. It is a pleasure to hold this ECT STAR colloquium together with my colleague Ralf Rapp. The title, Exploring high-muB matter with rare probes, is also the title of a workshop which was originally foreseen to be held in 2020, but was postponed to 2021 because of the COVID emergencies. The other organizers of this workshop are Tatiana Galatiuk, Maria Paola Lombardo, and Gianluca Usai. The study of the phase diagram of QCD is surely one of the most interesting fields in the study of strong interaction. And in particular, in this colloquium, we are going to concentrate on the region which corresponds to high values of the baryochemical potential. So in a short introduction, we will try to present some physics highlights related to this region of the phase diagram, and also to briefly sketch, let's say, the situation with the experimental programs. I will then leave the floor to Ralf, that will present a pure introduction to the study of hard and electromagnetic probes in this region of the phase diagram. This is what we mean with rare probes. And in a final part, I will discuss some foreseen or existing experiments, mainly at SPS and FAIR energies, which hopefully will allow us to shed light on this region of the phase diagram. So, which was and which is the aim of the workshop. Basically, we would like to gather theory and experiment communities which have two, let's say, complementary expertise. On one hand, we have a part of our community which is expert in studies of heavy flavors and dileptons, which is again what we consider as rare QGP probes. And we have also, let's say, a community that is especially interested in high-muB physics. These communities are not completely superimposed, so it would be useful to bring them together for discussion in order, in particular, to analyze the physics programs that are foreseen at the various facilities that are existing or planned. And on the theory side, we would like to boost the studies on these rare probes because these are still, let's say, at the very beginning in this specific energy range. We would like also to discuss the experimental programs and so also to identify and map out the potential complementarity between them. And one of the aims is, of course, to attract also interested groups towards the projects that are now starting. Of course, for the colloquium, the aim is, let's say, more limited. We will just now try to touch upon the main points that hopefully in person will be discussed later this year in the workshop. So let me start by saying a few words on the region of high-muB of the QCD phase diagram. And here you see another possible presentation of this QCD phase diagram. The axes are the temperature on the vertical axis, the baryochemical potential on the x-axis. And there are, let's say, basically two regions related to different values of muB. We have one region corresponding to vanishing of very small muB and high temperature, which can be theoretically studied by lattice QCD. And in this region, one has a crossover between a phase of nuclear of strongly interacting matter, which has hadrons as degrees of freedom, and the region where the deconfinement happens and one has a quark-gluon plasma. This transition is not a sharp one, it's more of a crossover, and you can also see here how the chiral condensate values decrease from the hadronic region to the quark-gluon plasma. And this is also, let's say, a rather gradual transition and corresponds to the restoration of chiral symmetries, which happens practically in coincidence with the confinement transition. In the region of large muB and more moderate temperature, one can perform a lot of interesting studies. And in particular, it is foreseen by models inspired to lattice QCD that a first-order transition is present instead of a rapid crossover between the hadronic and the quark-gluon plasma phase. And this first-order transition line should end in a second-order critical point. So there is indeed a large discovery potential for this region also because, as we will see, the amount of experimental information is for the moment rather limited. In this slide, we try to dress up these phase diagram with experimental points. These black points correspond to results obtained for the chemical freeze-out, namely this is the moment in the evolution of the collision where the abundances of the various hadron species are fixed. And one can see this evolution from the region of low muB to high muB and the corresponding temperatures. At low muB, these, let's say, freeze-out points correspond for what concerns the temperature rather strictly with the confinement threshold, while they go down when the baryochemical potential value is increased, and this corresponds, as we will see, to lower energy experiment. So in that specific region, there are various experimental challenges, and one, let's say, and most important is possibly to locate the precise onset of the quark-gluon plasma, and as we have already mentioned, detect the conjecture, the QCD critical point. To do that, we have various observables, and so one might measure the strangeness, and this, of course, helps to settle the chemistry of the system. By studying the charm quarks, one can analyze transport properties. Event-by-event correlation and fluctuation can help us in discovering a critical behavior of the matter. And finally, Dileptons can allow us to study the emissivity of matter. And these two red points that are here are indeed corresponds to the temperature that were measured by specific experiments, namely NA60 at the SPS and Hades at CIS GSI from the measurement of dileptons. One can see that there is, let's say, the region of NA60, which corresponds to energies top SPS, about 20 GeV square root of S. One is clearly above the temperature for the phase transition, while at Hades energies, which are of the order of a few GeV in the center of mass, we are clearly below this transition region. So we have an intermediate region which is now, for the moment, let's say, almost completely unexplored, for example, from the point of view of dileptons, and it is very interesting for these studies of the high-muB region. This is, let's say, shown very schematically in this slide, where again you see once more the phase diagram, and you see some of the experiments that had access to rare probes now or in the past, and in the collider region, which corresponds to high square root of S, we have experiments at LHC and RIC, such as Alice, Phoenix, and STAR. We had experiments like NA60 and Ceres at top SPS energy, about 20 GeV. The other experiment is, as we have already said, at a lower value of collision energy, and so explores high baryochemical potential. In the middle, there is a kind of terra incognita, because for the moment, almost no information exists for these rare probes. Now, the situation is such that there are indeed around the world a lot of planned facilities for the study of high-muB. Here they are grouped in these slides. This is, let's say, more for reference. I'm not going in detail to all of them. The message is that indeed there exist, or there will be existing, many facilities in various places in the world that will explore the region between low, meaning about 2 GeV in the center of mass, to high, about 20 GeV center of mass, and that therefore will fill the gap that we have seen in the previous slides. And also, because of their partial overlap in energy, they will allow an independent confirmation of the results. What does one need for the study of rare probes in particular? Of course, since these probes are rare, by definition, one needs high luminosity. And so this means also high interaction rates. And in this summary plot prepared by Tatiana, one can see the reaching collision energy and interaction rates of various processes, or various projects that are existing or that will exist in the near future. In red, you see collider experiment, and as you can immediately see, and as it is also expected to reach high interaction rates, one has preferably to go to fixed target experiment, which allow to work with very high beam intensity. It is also necessary to have, let's say, detectors with large acceptance and high efficiency, and also preferably experiment with triggerless running mode that allow indeed to have to collect a very high iterated luminosity. Substantial progress in detector technologies is needed for such a jump to go in the megahertz region for the interaction rate, and this is something which is taking place in this year. And of course, finally, one need also, from the point of computing, very performing equipments. Before going more directly to the study of rare probes, it is interesting, of course, to cite at least one example of an observable which is not related to rare probes, but that is known to probe the features of the QCD phase diagram. This is the study of the critical fluctuation, because indeed, let's say when crossing regions close to the critical point, one is expected to have diverging values for the susceptibilities and for correlation length. And these are expected to lead to strong fluctuations of conserved quantities, such as in particular the baryonic number. One way to study the situation is to look for observable discontinuities in the higher moment of particle number distribution. These can be investigated by means of a beam energy scan, and in particular it is interesting if one can go to study the higher moments, because they are going to more effectively probe the tails of the distributions. These are measurements that, of course, in order to go to higher moments, need a lot of statistics. And here I present some results on one of these moments that were obtained mainly at star, so with an energy scan between 200 GeV and down to about 7 GeV, and also with the measurement from ADES. One can see that, let's say, in case of the observation of such fluctuation, in particular, one is interested to a non-monotonic behavior as a function of square root of S, and the star results present an indication with a significance of about 3 sigma. So this is, let's say, already an interesting result that, of course, needs a confirmation with more accurate experimental results, which will come in the future. But it's now time to move to the study of hard and electromagnetic probes in particular, and so for that, I would leave the floor to my colleague Ralf, that will present a theory introduction to the specific observables.
So good morning, ladies and gentlemen. Thanks for joining, and thanks to Enrico for handing over the presentation for the second part of the colloquium, where I'll try to discuss the theoretical aspects of electromagnetic and heavy flavor probes at high baryon density in the context of heavy ion collisions. I will focus on thermal dilaptons and heavy flavor, in particular charm, and I will discuss for both first a little bit the general ideas underlying these probes, and then in a little more detail what we can do with them in the context of the heavy ion collisions in the 5 to 10 GeV energy regime. For the thermal dilaptons, I will discuss the chiral restoration and degrees of freedom, how they can be probed, and more specifically excitation functions to search for first order transition. While for heavy flavor, I will discuss the sort of underlying theme of trying to understand the QCD force, the basic QCD force at finite chemical potential, and what we can do with that at high baryon density in terms of excited charmonia and open heavy flavor diffusion. So let's start with the schematic of a heavy ion collision. Incoming nuclei colliding and with hard processes upon first impact, but then we believe that this system thermalizes locally rather quickly into possibly a quark-gluon plasma, which then expands, transits into hadronic matter, which will still keep interacting and cooling until we reach a rather sudden freeze of the strongly interacting particles. Now, the thermal dilapton radiation that I will focus on comes in basically from the radiation of the interacting phases, and we sometimes refer to it also as the excess radiation, as it is the kind of sources that go beyond what you would expect or have in a proton-proton collision. As it turns out, these dilapton measurements have never been made in this energy regime of 3.3 to 8 GeV. For heavy flavor, the idea is that these particles are actually produced entirely in the first collisions where there's enough energy, and then they can be used as kind of Brownian markers through their diffusion through the medium that is formed in these collisions. And in this way, we can access the transport properties of the medium. Also here, very little is known experimentally about these probes, but also theoretically, very little is known about the basic in-medium properties of the force at finite baryon density and, in fact, also in hadronic matter. So let's start with the thermal dileptons, where our main workhorse is this 8-differential thermal production rate. And this rate really has a rather straightforward structure. It is composed of the electromagnetic spectral function of the hadronic system and a thermal occupation factor carrying the energy of the lepton pair and the ambient temperature. Now, this electromagnetic spectral function is actually very well known in the vacuum from the inverse process of the annihilation of dileptons into hadrons, and it basically is characterized by two regimes. One is the low mass regime, where it actually nicely signifies the fundamental phenomena of confinement in mass generation, as it is really dominated by massive hadronic degrees of freedom in terms of the light vector mesons. On the other hand, at higher masses, above say 1.5 GeV, the rate becomes continuum-like. In fact, it's very well represented by perturbative quark-antiquark continuum, and the subsequent hadronization that has to occur in the vacuum actually does not affect the cross-section anymore. So in this regime, we can actually, the focus changes from the spectral function to the thermal occupation factor that will give us a handle to infer the temperature of the system in heavy ion collisions. So the questions we can then ask indeed are, what happens to these hadronic degrees of freedom in the medium? Can we find change in degrees of freedom by observing these dilepton spectra? And can we learn about the restoration of the chiral symmetry in the medium that I will elaborate more on later? On the other hand, at the high end, as I already alluded to, the continuum radiation can be used as a thermometer. In addition, it turns out we can go to a very low mass, where in the limit of small lepton pair energy and momentum, we can get access to a fundamental transport coefficient of the medium, namely the electric conductivity. And finally, the total yields of the dileptons being radiated throughout the entire evolution of the fireball should give us a handle, or at least an idea of what the total fireball lifetime in these collisions is. Now, before going into more detail, let me put the dilepton measurements into the context of the phase diagram of the strong interaction here shown in the temperature chemical potential plane. The black points are piece of information that we have extracted from hadronic final state spectra, in particular their chemical composition. And we already see here that we cover an impressive region of the phase diagram varying the energy of our collision system. But there's also been quite some activity on dilepton measurements shown here in some examples. For one at the high energy frontier, LHC and RIG, here shown a beautiful excitation function at RIG, all the way from 200 GeV down to 20 GeV, which then seamlessly connects to the SBS energy regime. Earlier measurements by the Ceres coloration in particular, here at 17 GeV, and also one pioneering measurement at around 9 GeV. On the low energy side, we have this beautiful data from the hardest coloration at a rudess of about 2.5 GeV, which also augmented earlier results from the DLS coloration at Beverlac from the 1990s. As it turns out, however, an important region of the phase diagram is not covered by dilepton measurements thus far. And this is, turns out to be the region of the phase diagram where we may expect a very interesting phase structures in terms of first order transition, a critical endpoint, or even more exotic phases. So based on our understanding that we have thus far for these dilepton spectra, it is a very compelling enterprise to go into this part of the phase diagram and explore whether we can find any evidence or any new kinds of phase structures. All right, with that, let me discuss one specific Dilapton measurement, the best we have thus far, to illustrate what we can do with this observer. From the theoretical point of view, which is the Ni60 dimuons at SBS, from the theoretical point of view, what we have to do is to integrate this differential rate that I wrote down earlier over the space-time evolution of the fireball, and usually also over momentum to arrive at an invariant mass spectrum. And following what I also indicated before, we have to basically account for the radiation from the quark-gluon plasma, typically done in terms of quark-anti-quark annihilation with alpha S corrections, and from the radiation from the hadronic medium, which is mediated by these light vector mesons, in particular the rho meson. So a key question then is, what happens to those hadronic degrees of freedom, to those vector mesons in the medium? And here I will use calculations that we have done quite a while ago with Jochen Wambach for the rho spectral function, also omega and phi in principle, which evaluated the modifications of the rho through interactions with the surrounding hadrons. And what we found at the time is that with increasing temperature and density, this vacuum rho peak really broadens very strongly to the extent that the resonance structure is essentially melted. So with these ingredients, we can now make a comparison to the beautiful Na60 excess spectra. And we indeed find that this combination of QGP and hadronic radiation gives a very good description. And what we can extract are first and foremost two things, namely that here in the low mass region, we see that the rho peak is essentially melted. There's a remnant, of course, still there, because we also have contributions from later phases where the rho comes back. But really at the highest temperatures of hadronic matter, this rho is essentially melted. On the other hand, at the higher masses, we can use the slope of this continuum radiation to extract the temperature. And very interestingly, the temperature, the average temperature here we extract is about 200 MeV, which is well above the temperature for the pseudocritical transition from hadronic into quark-gluon matter. So we're really producing a quark-gluon plasma, and we find that under these conditions, the rho meson melts. It is also noteworthy that the main effect in the melting of the rho meson is actually driven by the surrounding baryons. And that makes it, of course, very interesting to then pursue into the lower energy regime, where the baryon concentration increases relative to the mesonic one. Finally, what I will show in a little while is that we can use the absolute yields here in the low mass region also to infer the lifetime of the firewall. Before doing that, let me elaborate a little bit on the issue of chiral symmetry restoration. Now, to understand restoration, we first have to understand the breaking of chiral symmetry. So in the QCD vacuum, due to the formation in particular of the quark condensate, we expect or we believe that chiral symmetry is broken, and that manifests itself in the hadronic spectrum. In particular, chiral multiplets, which transform into each other under chiral symmetry, are expected to become split up, signifying the breaking of chiral symmetry. And there are several very nice examples of that in the observed hadronic spectrum indeed. One is the splitting between the pion and the sigma, the pion, of course, being the Goldstone boson of the spontaneous symmetry breaking. We see a strong mass splitting in the nucleon sector between the protons and neutrons and its chiral partners, the N-star 1535. And we also have a chiral partner of the rho in terms of the A1, which in the vacuum also split by a large amount, about half a GeV. Now, it turns out that for the rho A1 case, or vector axial vector case, there exist very nice so-called chiral sum rules, which actually quantify the chiral symmetry breaking in relation to the order parameters of chiral symmetry breaking. And that are these so-called chiral sum rules. And specifically what they tell us is that the different energy moments of the difference between vector and axial vector, this delta rho, so different energy moments integrated up yield chiral order parameters. So for example, if you take the 1/s moment, you get the pion decay constant, signifying the existence of the Goldstone boson, and thus the presence of the breaking. If we take the 0th moment, we get a relation to the quark condensate. If we take the 1st moment, we get a relation to the 4-quark condensate, the Chiral symmetry breaking 4-quark condensate. Now, the nice thing is that these Chiral sum rules remain valid in medium at final temperature and density. So what we tried then to do is to analyze these sum rules by using as an input the raw spectral function that we calculated and agrees with experiment on the left-hand side, and on the right-hand side we use information from lattice QCD for the temperature dependence of these order parameters. What remains is the axial vector spectral function that we try to infer then from these sum rules, and that is shown in this plot here. So starting from the vacuum, we then were able to find a solution for the axial vector spectral function that is compatible with the input raw and spectral function and the lattice QCD data, and it illustrates how the mechanism of chiral restoration is realized, which appears to be that the A1 also melts, but it in particular also comes down in mass. The A1 comes down in mass to the ground state of the multiplate, in this case, the raw meson. And indeed, this seems to suggest that the mechanism of chiral restoration is not a generic vanishing of the masses, but rather a burning of the mass splitting that you have in the vacuum, accompanied with the resonance melting. In fact, similar observations were made in other theoretical approaches. There are very nice lattice QCD analysis in the baryon sector, which also show that basically the excited state moves toward the ground state and degenerates in this way. And there are also randomization group analysis of effective chiral models, which show, again, a very similar mechanism in the pi sigma and, in fact, in also the raw A1 channels. All right, so let me then move on to the excitation functions. And here I plot on the left-hand side the total yields of the Dilapton radiation for central heavy ion collisions, say gold-gold collisions, as a function of collision energy integrated in this low mass region. And what we find is the following. The total yield, the total thermal yield integrated over this region composed of the hadronic and the QGP indeed turns out to trace very well up to a normalization constant the lifetime of the fireball. So indeed, the total yields are tightly correlated, in fact, quantitatively reflective of the lifetime of the fireball that you form in these heavy ion collisions. As for the higher mass region, where we have this nice thermometer, we investigated the excitation function of that extracted temperature. And right now there have been only 2 measurements, in fact, by the Na60 coloration, this 200 MeV I referred to earlier, and by the hardest coloration. And we don't really know what happens here in that transition region. So we have done theoretical calculations here based on what we understand now, but really depending on what the phase structure is, we expect there could be interesting features. The baseline would be if there are no interesting features schematically, that there's a gradual transition between the higher energies and the lower energies in both temperature, also in lifetime. In fact, the lifetime increases a little bit at the lower energies because the fireball is less explosive, so its acceleration, if you wish, is a little lower. So that is understood. But the exciting possibility is that there might arise non-monotonic features in both excitation functions if, say, a first order transition develops. And I schematically show that here. What one could find, this is again speculation, and one has to do more precise calculations in the future. If there's really a first order transition developing, one could expect to develop a plateau, much like the caloric curve that has been done in low energy heavy ion collisions. Along with that first order transition, one would expect that the lifetime increases significantly, which might in fact develop a maximum in the emission of these low mass dileptons. And indeed, there are recent theoretical analysis that show that this increase to the first order transition could be up to a factor of 2. So there's good reason to believe that the dilepton measurements really have a very good sensitivity to any non-trivial features of QCD phase structure in this energy regime. Okay, with this, I will move on to the heavy flavor sector and elaborate a little bit how we can use heavy quarks to probe the in-medium QCD force. So in the vacuum, we know very well the QCD force between two static charges, say two heavy quarks, heavy quark and underquark. And indeed, this linear part of the heavy quark potential is maybe one of our best known manifestations of confinement in hadronic systems. And on top of that, this so-called Cornell potential, now accurately verified also in lattice QCD, yields a very precise spectroscopy of the germanium and epsilon states, at least the standard ones, not the exotic ones. Well, that's why we call them exotic. Excuse me. Now, at finite temperature, we expect the heavy quark the heavy quark potential to be modified, and indeed, we have a very nice lattice data, zero chemical potential for what is in fact the free energy of a heavy quark pair. That indeed shows how this quantity gets suppressed, screened, as you increase temperature. Now, the free energy is not exactly the potential. It's a combination of internal energy and entropy, and one has to work a little harder to really extract a potential from that. But we have made good progress on that in the high energy context. But clearly, if you want to probe the phase diagram, we should ask the question how this heavy quark free energy or the in-medium heavy quark potential develops into the finite chemical potential plane. And experimentally, we believe we can actually test that by elaborating and then calculating the consequences for heavy quark and quark-cornium transport in heavy ion collisions and compared to experiment. Now, in this lower energy regime, remarkable features are among the sensitivity to finite μB, also the fact that the hadronic phase relatively becomes longer than the QGP phase. So we have a better sensitivity to hadronic medium effects, which in turn will also be beneficial for the high energy extraction of transport properties, where the hadronic phase will also play a role. So any precision extraction at high energies will also eventually have to deal with the hadronic medium effects, for which in turn we have a better sensitivity at lower energies. So let me elaborate on the heavy flavor part with two examples for germanium and open heavy flavor. So for germanium, the basic theoretical quantity is much like in the light vector meson sector, the spectral function of the state here for the germanium 1- showing, well, in the vacuum we have this J psi and the psi prime, but in the medium we expect here from this calculation, taking as an example, that indeed that with increasing temperature the state eventually melts. And that is expected as the potential weakens, the binding energy will decrease, and at the same time we have dissociation processes which are related to the width, and ultimately they become so strong and the binding energy so weak that the states will melt. The way we implement that into transport calculations for heavy ion collisions is illustrated here with this relatively simple rate equation, and you see that the main transport parameter here is indeed this inelastic reaction rate, which leads to suppression, but in principle can also lead to regeneration once these states come back into existence. Regeneration meaning recombination of charm and under-charm quark into these resonance states. Now, both of these transport parameters essentially depend on the in-medium heavy quark potential. And this is the way then how we make the connection to the in-medium QCD force. Specific features in this lower energy regime that I want to point out is, again, the importance of the hadronic phase, but also the fact that the J psi itself, in fact, may be not so much modified in these lower energy collisions. So, for example, this calculation shows that even at a temperature of 200 MeV, the J psi may still be relatively narrow. Indeed, this has been is compatible with the information we have from SPS measurements at 17 GeV, that the suppression we observe there is really from the primordial so-called nuclear absorption, not so much from the medium. While on the other hand, the psi prime shows a very strong modification. In fact, it's already gone slightly above TC. So for the excited states, we really expect much more strongly modified production yields. And indeed, that has been indicated by SBS data here shown in terms of the psi prime over psi ratio as a function of centrality here for the proton-proton value, which then as you go to central lead-lead collisions is strongly suppressed. So excited states will be a very interesting observer to learn about the medium effects in the spectrum, maybe even exotic states like the X3872. Now again, key ingredient here is the interaction of the individual quarks in the quarkonium with the medium. So you might actually argue that if you take one quark away, you have a little simpler problem, and that is actually the problem of heavy quark diffusion in the medium. So let me elaborate on that again. So because of large mass scale relative to the temperature that the heavy quarks provide us with, what we're dealing here is really the equivalent of Brownian motion, many little momentum transfer interactions of heavy quarks in this quark-gluon plasma, mostly via elastic interaction, because simply there's very little energy transfer, so radiation is strongly suppressed. Another benefit of this large mass scale is that thermalization of the heavy masses is delayed. So we can expect that charm and certainly bottom spectra contain a memory of their interaction history. And if they do, then we have a direct gauge of their interaction strength in the medium. And that allows us ultimately to extract the transport coefficient from diffusion calculations because they do not thermalize. So deviations of their spectra relative to the baseline, say PP spectra, give us this measure of how strongly they interacted. And this heavy quark diffusion coefficient is a fundamental transport coefficient of the medium, much like, say, the viscosity or the electric conductivity, and is, of course, of high interest to investigate all of these transport coefficients and establish relations between them, because, after all, we expect that the basic interactions that the heavy quark or the light constituents or the charge constituents undergo in this medium should be related through the basic interactions in medium interactions in the system. Now, technically, how we model heavy quark transport is through a Fokker-Planck equation in the spirit of this Brownian motion that evolves this heavy quark distribution function basically in terms of two transport coefficients. One is the thermalization rate, the other is the momentum diffusion coefficient. And they're actually given in terms of this transition rate for the heavy quarks, weighted with their momentum transfer to the first power for the rate and for the thermalization rate, and to the second power for the momentum diffusion coefficient with that same transition rate. Now, that actually implies that these coefficients are related through this famous Einstein relation, so they're actually not independent. And in fact, this kind of relation is theoretically very valuable to test your approximations that you may want to apply in the process of doing the calculation. On top of that, both of them are related, at least at zero, in the zero momentum limit, to this diffusion coefficient. Now, the key ingredient to this transport coefficient is this scattering matrix, the heavy light scattering matrix, that gets weighted with this angular factor in thermalizing the particles and convoluted over light quark distribution functions. Now, this heavy light scattering amplitude, that is the one that then ultimately is again related to the force that the heavy quarks feel in the medium, and this ties back into finding out how the basic QCD force determines the transport properties and ultimately the extracted value of the heavy quark diffusion coefficient. So let me give you a couple of examples here pertinent to the low energy regime. Clearly, what we want to do is we want to map out that ds into the phase diagram. We have already learned quite a lot, sort of compiled in this plot at zero chemical potential from the high energy domain by analyzing D meson spectra and such at the LHC and RIG. And what we found is indeed that we want to do any justice to the data. We have to have very strong interactions. So, for example, this perturbative calculation, even with a rather large alpha S, will be far away from data. Even if you use the free energy that I showed earlier as a potential proxy, it's not enough interaction strength. You really have to go to sort of extremes like here for the internal energy to get into a regime where we can describe the experimental observations of the modified D-meson spectra, or we use perturbatively motivated calculations, but they have to be stronger than the baseline Born diagrams by a factor of 10. Then we can really describe data, and this is another very strong indication that we're dealing with a strongly coupled medium at zero chemical potential. But of course, we should ask how that property migrates into the QCD phase diagram, into the finite µB plane. Do we also have a strongly coupled medium, and how does it develop with µB? On top of that, even at high energies, we need to have some control over the hadronic phase, which should continuously connect to the QGP, because after all, we're dealing with a crossover transition. So there should be no discontinuity. And even at high energies, the hadronic diffusion will play a role quantitatively in the extraction, in any precision extraction of the diffusion coefficient. And the point here being that if you go to lower energies, the importance of the hadronic phase relative to the QGP will increase. And in this way, we get actually better sensitivity to the hadronic medium effects. As for the phenomenology, at these low collision energies here, root S of about 7 GeV or so, I have some very interesting features because of the finite chemical potential. One is that charm and D-mesons are actually differently affected than anti-charm and anti-D-mesons, depending whether you're in the QGP phase or in the hadronic phase. For example, in the QGP or through hadronization, we expect the anti-quarks, the anti-charm quarks, to have a stronger interaction strength as they can recombine or resonantly scatter through the quarks in the system, which are more than the anti-quarks. On the other hand, in the hadronic phase, it turns around. The D-mesons have more opportunities for rescattering because they can excite states which resonance states which have charm quarks in them. So in the hadronic phase, the D-mesons are actually more modified. So that gives us another discriminating tool for disentangling the sort of photonic and the hadronic effects in the diffusion. Now, one very nice example of a calculation of D-meson spectra in these low energy collisions relative to the spectra you have in PP collisions is here shown by the Frankfurt group. And what turns out here is that this ratio shows actually a very interesting feature in terms of almost a divergence of the D-meson spectra once you divide it by the PP. And the reason is not the divergence of the AA, but that the PP spectra are limited by kinematic limits through the energy you have in the production process of a PP collision, which are 1.6 for the D-meson in momentum and 2.1 for the anti-D, which can go further out because the production threshold is smaller, because you can do it with the lambda C, not with the D Bohr. And what then happens is in a heavy ion collision that there's momentum diffusion beyond that kinematic limit, and that creates really that increase here, that you have finite amount of D-mesons beyond the kinematic limit that you reach in PP collisions. And that would, of course, give a very nice handle on quantitatively on the diffusion properties of charm in these lower energy collisions. And with that, I'm done, and I hand over again to Enrico for the third part of the colloquium. Thank you very much.
Thank you, Ralf, for this very interesting review of the main theory topics of this colloquium. I will now continue with a short review of some experimental studies which are foreseen, in particular for dileptons and for heavy quarks. So, as we had seen previously, there is a kind of terra incognita between the low energy range covered by an experiment like HADES at the CIS 18 accelerator of the order of 2 GeV, and top SPS energy, which was covered by an experiment like NX60. This hole is likely to be filled in the next few years, in particular by two projects, by 2 experiments that are now being either built or discussed. And these are CBM at the FAIR facility at GSI and Na60 Plus at the CERN SPS. It is interesting to note that these have a very complementary coverage, because the CIS100 facility at GSI will run up to about 5 GeV energy, which is more or less where the coverage of the SPS starts. So before going to discuss these two projects, let's start from an existing experiment, in particular from HADES, which is installed at the CIS-18 accelerator always at GSI, because this is an experiment that is contributing in particular for the study of dileptons. It is a fixed target experiment, of course, which accelerates not only ions, but let's say studies also proton and pion-induced reaction. It has a full azimuthal coverage with also a large polar angle coverage. It is a spectrometer, so based on a toroidal field with tracking devices and with an electron identification, which happens also in front of the tracking. The main focus is on heavy ion collision, and so with observables like event-by-event correlation and fluctuations, flavor productions, but in particular dileptons. And then, of course, since the study of dileptons in the low mass region also happens to intermediate mesons like the Rho, it is very interesting to have complementary measurement induced by pion beams, for example, that helps decoding the electromagnetic structure of baryons in the time-like region. And of course, proton beams are important for other reference measurements. One of the most interesting results is shown here in this left plot. It is the dilepton spectrum after subtraction of the hadronic cocktail in the region between 0.2 and 0.8 GeV over C square. And one can see that this spectrum can be reproduced using the thermal emission rates for dileptons folded with a model for the medium evolution. So this result shows that in this gold-gold collision at 2.4 GeV, one has radiation emitted from a relatively long-lived source in local thermal equilibrium with a temperature of slightly more than 70 MeV. There will be, let's say, further studies in the future and further results, and in particular studies of the polarization and of the flow of these dileptons will be carried out and allow us to understand more in detail the feature of this production. Complementary to that, and as mentioned at the beginning, studies of pion-induced reaction on protons were performed. Here, this is interesting because it allows us to investigate how the Rho meson, an intermediate Rho meson, couples to baryons. And these results show that indeed the contribution like the one of the Rho are essential for interpreting these results, and so reinforce the role of vector meson dominance, and also allows us to investigate more complex models of the structure of a nucleon as an object with a core surrounded by a mesonic cloud. HADES is still taking data and will take data for still some years. There has been a high statistics data taking with silver-silver in 2019, and here you can see a preliminary dilepton spectrum. It is interesting to note, apart from the large statistics, the fact that it shows entries well above the nucleon-nucleon threshold, showing that indeed there is a very interesting dynamics also in this sub-threshold production that can be indeed studied by this kind of experiment. maybe even more interesting is, let's say, a further study that is foreseen. Let's say, this comes from the fact that the dense baryonic matter, which is produced in an experiment like this one, is similar to the one that is expected in binary neutron star mergers. Indeed, these lines here show the evolution of the matter produced in gold-gold collision at the energies reached by Hades in the temperature baryonic density plot, and these triangles represents the same regions in the QCD phase spectrum phase diagram, which are reached by or that can be simulated in simulation of binary neutron star merger. So one can indeed try to attempt laboratory studies of the matter properties in compact stellar objects, obtaining information on the equation of state. But let's now move a bit more into the future, not too much. Here you can see the excavations and the working for the new facility FAIR at the GSI, and this hole that you see here is the experimental hole where the CBM experiment will be installed. CBM is a rather large experiment, and it has also a rather, let's say, complex setup. Its main feature is the need of sustaining very high event rates from 10 to the 5 to 10 to the 7 Hertz, which is necessary for rare probes at relatively low energies. And so this needs also fast radiation hard detectors and also similar properties for the front-end electronics. There are two main, let's say, setups, one so-called the Electron Setup and one called the muon setup. We will come back to that in a moment. And all the detector is complemented also by the Hades experiment itself that will be coupled to the CBM detector. All in all, this is well on track for the day one, let's say, data taking, which should happen in 2025. For the measurement of dileptons, there are, of course, simulations that are done. Here you can see typical generated spectra for both the plus E minus and mu plus mu minus final state. These are obtained in the, let's say, the standard way by generating hadronic cocktails, which include the various decays of pseudoscalar mesons and vector mesons, and these are complemented by a simulation of thermal radiation, starting from the electromagnetic emission rates and folding with the evolution of the collision. And here you can see indeed these two simulations that refer to gold-gold collision at about 3 GeV square root of S. Just a quick view to the foreseen setup for the so-called muon setup. One has the difficulties of dealing with muons down to low energies. This is, let's say, tackled by having a hadron absorber which has some intermediate tracking layers in order to detect also these low momentum muons. And then with the triple gem detectors, one performs the effective tracking in this region. Of course, the signal over background ratio is better in the cases where, let's say, the muon pass through the whole, let's say, absorber. But the measurement can be performed also with other topologies where also, let's say, kind of short paths inside this absorber are detected. And here on the right, you can see a typical invariant mass dimuon spectrum in the region of, let's say, low and intermediate mass region. Moving to the electron setup, here you can see a sketch you see the microvertex detector for the detection of the offset with respect to the interaction point, the silicon tracker system, and the identification, which is done via reach and then complemented by the other CDM detectors, TRD and TOF. Here, let's say a difficulty is let's say, originated by the fact that there is additional background due to the material budget in the tracking system before the identification of the electrons. This is tackled with having a good pion discrimination and reducing directly this electron background by reconstructed the pairs from gamma conversions and pi-zero Dalitz decay employing the topology cuts. Here on the right, you can see an invariant mass spectrum, again, in this low and intermediate mass region. It corresponds to 5 million events, which should be obtained in just 3 minutes of beam at 300 kilohertz interaction rate. Of course, let's say one wants not to detect only Dileptons, but open charms, because this is, of course, one of the probes that we are dealing with in this colloquium. It's very interesting also in this frame, where one would be basically in the region which is close to the threshold or even sub-threshold for gold-gold collision. This detection will be performed using the monolithic active pixel sensor, the silicon tracking station, and it can be demonstrated that in the typical data taking of 4 weeks, it would be possible to collect decent statistics in ion-ion collision. Here you can see nickel-nickel at 15 AGV, which allows more than 600 D meson in about 4 weeks. And also in proton-nickel collisions, giving in this way a reference for these studies. Let's now move to higher energy, to the SPS. The CERN SPS can cover the energy region between about 5 GeV up to top energy, which is about 17 GeV, and can deliver ion beams with a very good luminosity. And as we already mentioned, it gives a good complementarity with respect to the energies that will be reached at the CIS-100 at FAIR. At the SPS, there was a very strong heavy ion program, which, however, concentrated mainly on top energy measurements. In the low energies, for the so-called rare probes, almost no results exist, except an indication for an access in the Dielectric Spectrum in the raw region, which was obtained by the Ceres experiment at 40 GeV incident energy, which shows that indeed there is interesting physics in this energy range. After the Ceres experiment, in the last part of the SPS program, there was a third generation experiment called Na60, which measured dimuons and could reach an unprecedented precision on the measurement of electromagnetic probes, but could also study at the same time J-psi and open charm via semi-electronic decays. It was based on a large muon spectrometer, which was separated via an hadron absorber from a vertex spectrometer close to the target. And by matching the muon tracks in the vertex spectrometer and in the muon spectrometer, it was possible to reach a very good resolution for this measurement. This very concept is now used to design an experiment which will be able to cover the whole SPS energy, and that is called now Na60+. This is the layout foreseen for the Na60+ experiment. Here one has the muon spectrometer based on a toroidal magnet and on several tracking stations, complemented by station which can be used as an identifier for muons or for triggering. an absorber which separates these muon spectrometers from this vertex region in a dipole field. And in this vertex region, one has the vertex telescope based on monolithic pixel sensor. A very important point is that this muon spectrometer length will have to be varied in order to cover mid-rapidity at different collision energies. Very quickly, some information on the R&D for this experiment. For the muon spectrometer, a design has been prepared for the toroidal magnet, and a prototype is being built, while for the dipole magnet, an older CERN magnet will be reused. Maybe more interestingly, for the vertex spectrometer, thanks to the synergy with the ALICE inner tracker system 3, the sensor development is taking place, and this will allow reaching, let's say, very good performance for what concern the interaction rate and the maximum particle rate that can be achieved, and the detector itself will be very granular, and thanks to a stitching procedure, very large chips will be constructed. The optimization is for the moment in progress, and also in progress is the project of the muon spectrometer chambers, and this will be based on GEMS, which have requirements that fulfill the needs for the experiment. And the first R&D step will likely be to build the first prototype for these detectors. As I was mentioning, it will be important to access mid-rapidity at different collision energy, and so the muon spectrometer will have to be mounted on rails, and the thickness of the add-on absorber will be adjusted following the energy of the beam. The installation is foreseen now in the H8 line of the CERN SPS, which can deliver beam intensities of 10 to the 7 per 20-second spill, with a let's say interaction rate likely of the order of 10 to the 5 per second in average. A few words about the performance. So here you can see the PT versus rapidity coverage for dimuons emitted from the QGP phase in the region of mass larger than 1 GeV. Here one can see that one can reach the region close to mid-rapidity with an acceptance for pi which is larger than 1%, which is a reasonable and comfortable number, and the mass resolution for the resonances, which varies from about 10 MeV at the omega to 30 MeV at the J psi, which represents a factor 2 improvement with respect to the old NH60 experiment. The Dielecton spectrum has been then simulated. Here you see the results of such a simulation. In 1 month, the experiment should be able to take about 4 million dimuons for central lead collision. This is a factor 20 improvement with respect to the old NH60 experiment, which studied minimum bias indium-indium collision, and will allow, therefore, having a very good statistics for, in particular, for this intermediate mass region, where the measurement of the slope and therefore of the temperature of the system can be attempted. This is shown in more detail in these slides, where one can see the sources that are present in this intermediate mass region. Of course, it will be important also to measure the Drellian, and this contribution will also be estimated with the help of dedicated proton nucleus measurement. The important figure of merit here is this about 2% uncertainty on the evaluation of this slope of the intermediate mass dimuons. In this way, it will be possible to build a kind of caloric curve for the Dilapton production, and by coupling results from NH60 plus to results from CBM, it will likely be possible to have an accurate mapping and therefore a very strong sensitivity, for example, to possible flattening due to the presence of a first order transition. Moving to hard probes, and in particular to open charm and charmonium, open charm will be can be reconstructed, can be, let's say, measured in the via semi-electronic decays, but hadronic decays could also be reconstructed in the vertex spectrometer. And here you can see some performance studies at top SPS energy and at lower energies for the measurement of the D0 kappa pi decay. This plot is equivalent to 30 days data taking. And also it is foreseen to have measurements of charmed baryons like the lambda C, and also strange charmed mesons like the DS. And so these additional states will help, for example, in the study of the hadronization mechanism at this low energy. All in all, this gives good prospects for a first low energy measurement of charm in nuclear collision. Similarly, for the JAPE side, there is a strategy that is developed. In proton-nucleus collision, a measurement will be performed to calibrate nuclear matter effects that are very important in this energy range. They will be then extrapolated to lead-lead and compared with the actual data. And so one can see here that, for example, a scenario where an anomalous suppression sets in and then reaches about 20–30% can be easily recognized. So here the idea is to reach a good sensitivity to the onset of the JAPE side suppression. For less bound state like the Psi2S, a similar study will be performed. This is more difficult because there is basically a factor 100 less Psi2S with respect to the JAPE Psi, but still, at least maybe not to the lowest energies, but at least to fairly low energy, these studies will be performed. Just a couple of words on the development of the project. The discussion started already a few years ago, and they are going through the CERN, let's say, approval chain. In 2019, an expression of interest was submitted to the SPSC, and the aim is now at the end of 2021 to submit a letter of intent for the experiment. The goal would be to be able to start data taking after the long shutdown 3 of the LHC, and this will likely be around 2027. I can go now proceed to the conclusion. We hope to have shown that the investigation of the high-muB region of the QCD phase diagram is a hot topic in the study of strong interactions. This, let's say, was indeed rather clear. What in particular we tried to concentrate upon is the study of rare probes, to show that this is very promising and that at the same time there are non-negligible theoretical and experimental issues. On the theory side, Ralf has shown that using Dilaptons is really a kind of precision tool for searching for the first order transition and also to test mechanisms of chiral restoration. And also one could study transport properties of the medium by going to measurement of open charm and charmonia, both ground states and excited. On the experiment side, there are experiments like CBM, which are being built or that are being proposed like NA60+, and these have the potential to fill the gap between top SPS energy and the lowest hardest energies. So all in all, we feel it is now really time to gather the experiment and theory community in order to finalize the physics programs and to prepare a detailed plan of measurements, and hopefully these will take place this October at the ECT STAR workshop exploring high-muB matter with rare probes. So thanks everybody for the attention. Goodbye.